Hi, it's Paul Bamberg here to tell you about linear regression for Math 156. But before you watch this video, there are two things you need to do. First, this script covers the example of spruce trees from sections 9.1 and 9.2 of the textbook. You'll want to read that and then have it open because I'm going to replicate some of the graphs that are in there. I'm going to be using formulas that are derived in those sections, and they're done in the math notes. So I would strongly recommend watching the math notes video before getting started on this. Okay, we're ready to get going. You have watched the math notes video, right? And you're familiar with the black spruce data. So we're going to read in data about these spruce trees, and this is data for a modest number of trees, including things like change in height and change in diameter. And we're specifically interested only in two of the columns, the one that measures the change in height and the one that measures the change in diameter. So I'm going to save those as vectors with their own short names. And the question here is, if the diameter goes up by a lot, does that mean the height is likely also to go up by a lot? And a simple way to try to guess the answer to that question is to do a scatter plot. You can find this scatter plot on page 249 of the textbook, and it does look as though a big value of ht means a big value of di. We might as well add lines, horizontal for the mean diameter, vertical for the mean height. And now you can argue that these two variables are correlated because there are lots of points in the northeast and southwest quadrants, comparatively few points in the other two quadrants. And one way of measuring this is calculating the covariance, which you have known for a long time is the expectation of the product, x times y, of the random variables minus the product of their expectations. And you know that this is 0 for independent variables, but that the converse is not necessarily true. R will happily compute this for us. There it is, 17.81891. And what does that tell us? Well, not much. It's positive, which confirms our impression that a bigger height goes along with a bigger diameter, but the numerical value doesn't really mean much. Before I explain to you how to normalize this, a word of warning. You might foolishly have computed this result by taking the expectation of the differences from the two means, and you get something that's a little bit smaller, 17.57 rather than 17.81. Why? Because what R does for you is to compute an unbiased estimate of the population covariance based on the sample covariance. I can replicate the value that R computes by taking the sum of the product of how much the height differs from its mean by how much the diameter differs from its mean, and then dividing by n minus 1. So there's 17.81. Or there's a quicker way to get the answer. This is a formula that's proposition 9.1 in the textbook. You don't have to subtract means from every individual measurement, but you've got to be a little bit careful because of this business of dividing by n minus 1. So there's another way of getting 17.81. If I bind these columns into a matrix, remember what cbind does. It takes two vectors and uses them as the columns of the matrix. Then the COV function will give me the entire covariance matrix. What are the diagonal entries? Well, you can see those are the variances of the height column and the diameter column, respectively. What are the off-diagonal entries? The off-diagonal entries are just the covariance that we calculated earlier. Now, here's a way of computing a number that's easier to interpret. We take the covariance and divide by the product of the standard deviations. And now, this is proved in the math notes, we get a number that has to lie between -1 and +1. This is the correlation. Here it's 0.9, pretty close to 1, a pretty high value, which shows that the increase in diameter is strongly correlated with the increase in height. There's a built-in function for doing this, which you'll probably find quite useful. When you're computing the correlation by hand, you have to compute things from the sample data. And it turns out, this is another thing that's proved in the math notes, it doesn't make any difference whether you divide by n or by n minus 1, as long as you do the same thing in the numerator and the denominator. Okay, now let's do some least squares regression on these two variables. Derived in the math notes is the formula for the slope of the so-called regression line, the line which best fits the data. And also derived in the notes is the formula for the intercept of that line. So let me put the regression line on the plot. There it is. And that line has the property that if you take the vertical distances from the various points to the line, square those vertical distances, and sum up all the squares, you get a smaller number for this regression line than for any other line. Of course, this is such a useful thing to do that R has to have a built-in function. I believe that LM is short for linear model. And if you call the LM function on the appropriate columns from the spruce data, bingo, you get exactly the same coefficients. You can see the intercept coefficient is minus 0.51, and that number is just disappearing off the top of the screen. If you want to fit the data more closely, R has a function that lets you, if you use df equals 3, fit a cubic polynomial to the data. I plotted that in blue. Now, a famous physicist said about 50 years ago, give me 3 parameters and I can fit an elephant, give me a 4th and I can make him wiggle his trunk. And it's certainly true. If you use a polynomial of high enough data, you can fit these data of high enough degree, you can fit these data perfectly. But a good use to which to put this cubic spline approach is the following. If the curve you get by using a 3rd degree polynomial doesn't differ by too much from the linear regression line, then this linear relationship fits the data pretty well. Now, as I said, we chose the slope and intercept coefficients, b and a, to minimize the sum of the squares of the so-called residuals, the difference between actual and predicted values. And I can easily make a vector of the predicted values. That's just obtained by, for each entry in the height vector, taking a plus b times that entry. If I plot the predicted diameters, of course, they lie right on the regression line. For each hollow circle on the diagram, there is a solid green circle, which is the predicted value. It's perfectly easy by subtracting vectors to get the distance, the difference between those, the so-called residuals. We can plot those too. That's the plot of diameter against height with the regression line shown. Here is the plot of the residuals, and not surprisingly, those residuals are centered on 0, and if I want the best fitting line, it's a horizontal line with an intercept of 0. We can make the sum of squares a little bit smaller by, as you've seen, using a cubic polynomial. But this is another way of confirming that linear regression fits the data pretty well. Don't forget, when you change the graphics parameters, you should always reset them back. Otherwise, the next plot that you make is going to be smaller than you wanted it to be. Now let's try splitting up the variance of the changes in diameter. There's the variance of the diameter vector, 3.19, and that variance would be non-zero even if the diameter change were precisely a function of the height change, say the height change multiplied by 1.5. So if I look at the predicted values, the green values in the top plot, they're not all equal. They've got a variance. And in fact, when you look at that variance, it's 2.6. So you say, that's interesting. An awful lot of the variance in diameter increases is just a result of the fact that these spruce trees had different increases in height. What's left is the variance of the residuals. And not surprisingly, when you add together the sum of the two pieces, you get the variance in the diameter vector. Problems in the book make much of the fact that the fraction of the correlation the fraction of the variance that's explained by the regression line is the square of the correlation. This ratio is called capital R squared, and you'll see it in many of the homework problems. Let's compute it. It's the variance in the predicted diameters, VPDI, over the total variance in the diameters. And I can calculate that along with the correlation squared of height and diameter. I get the same number, 0.81, in both cases. Next, let's take a different view of linear regression, a maximum likelihood approach. This is going to lead to exactly the same regression line, but it's going to need much stronger assumptions, which will turn out, in fact, not to be satisfied for our spruce trees. We're going to view the heights now as a fixed vector, not a random variable. Previously, the view was we've got a random selection of spruce trees from a large population of spruce trees, and each of them had a height change and a diameter change. But now we're going to view the heights as fixed. And we're going to make a linear model. The diameter is a linear function of the height plus a random residual that might make it larger or smaller than the predictive value. But here's the additional assumption. We're going to assume that all these residuals are independent, and furthermore, that they're all normally distributed, each with the same variance, so that this rules out the possibility that large spruce trees might have residuals with greater variance than smaller spruce trees, or that if a spruce tree of a certain height has a positive residual, there's a higher than average probability that one with a height very close to that will have a positive residual. In order to analyze this, I need the maximum likelihood functions in R, and that requires the stats4 library, which you've probably already installed. And as is done on page 269 in the textbook, we construct the negative of the log likelihood function. This is the probability as a function of the two parameters alpha and beta. They used to be called A and B for the regression line, plus the variance of the residuals that we will generate the observed data. And now we can use standard maximum likelihood techniques to get the estimates of alpha and beta. And you probably haven't memorized these results, but take my word for it, these are the same as the alpha and beta that we got from the least squares. That's one of the points of the proofs for this week, that this maximum likelihood approach gives you the same regression line as the least squares approach. But you may recall, if, as I suggested, you went through the proofs first, that this approach gives you one more parameter. It gives you an estimate of the variance of the residuals. Now, we computed the variance of the residuals from the data, and it turns out that our assumptions in this model are not well satisfied. If you look at the histogram of the residuals, it really doesn't look as though those data come from a normal distribution. And if you go back to MLE, remember that number 0.595. If you go back and look at the best estimate of sigma squared, it's 0.37, quite different, and that's a consequence of the fact that the assumptions for this model are not well satisfied for our data. This is not in the book, but being at heart a mathematician rather than a statistician, I can't resist generating some data where I'm sure the model is satisfied and making sure that in that case the maximum likelihood estimate of the variance comes out pretty close to my parameter. So let's generate some fabricated data, intercept of 0.6, slope of 0.3, and residuals generated all with a variance of 0.2. We need a fixed set of heights, but they don't have to be uniformly spaced, so I'll just generate 100 random numbers in between 0 and 7 from a uniform distribution. And then I will fabricate some height data to go along with that by taking a plus b times x and adding on a random, normally generated random variable where the variance is s, and therefore the third parameter is the square root of s. So now I've got a vector of x's and a vector of y's, and I can do the standard regression line stuff. Here is the shortest syntax for doing this operation in R. And you say, what? You put in 0.6 and you got an intercept of 0.7. What went wrong? Nothing went wrong. These are sample data. You've known for a long time that if you draw a sample from a population with a certain mean, the mean of the sample is not necessarily going to have the same value, and that's all that's going on here. I can plot my data and plot my regression line. Now let's try the maximum likelihood approach. And the question is, will we be able to get back not only an alpha and beta, which are pretty close to our original A and B, but also a sigma squared, an estimate of the variance parameter that's pretty close? Well, here goes. It took me a while to find out how to do this. When I get the results back, I just want the coefficients, and if I do results at sign coefficient, now I've got alpha, beta, and sigma squared stored nicely in a vector. Now let me calculate the variance of the random residuals. I do that by taking the y vector, subtracting off a plus b times the x vector from it to get a vector of residuals, and then taking the mean of those results, and I got 0.24. If, on the other hand, I look at the mean of the calculated residuals, I get something that is remarkably close, and both of these, you will see, are quite close to the S, which was 0.2, that I put into the model. So for the maximum likelihood estimation approach, if the data fit the rather strong assumptions, you can get a good estimate of the common variance of all the residuals. But for real-world data, usually those assumptions are not well satisfied. Let's have a look at a histogram of the residuals. In this case, it looks a little bit more like a normal distribution. And in this case, because of the nature of the model, if I had generated enough points, it would fit very neatly with that normal distribution. And we are done with this topic.